This is the second episode of Poke A Mon, where real science meets the Pokemon universe. I'm Chuka Wobodo, but you can call me Professor Baobab. My expertise is in science communication. You can sign up to my weekly newsletter below to get access to a free step-by-step guide on how to master any subject so you can explain it with ease. Disclaimer: this podcast is in no way affiliated with the Pokemon Company, Game Freak, or Nintendo. I am using Pokemon as a pedagogical tool as it pertains to tangential learning. In other words, I tell stories using Pokemon to capture the attention of those interested in Pokemon while remaining integral to the presentation of scientific knowledge. Today, we'll be talking about black holes. Black holes are regions of four-dimensional space-time where that space-time becomes so distorted that nothing which can move at or below the speed of a light can escape from them. We will talk about their formation and several key features such as the event horizon, singularity, the Schwarzschild metric, space-time itself, and the accretion depth. In the Pokemon games, it is said that Gardevoir has the psychokinetic power to distort the dimensions and create a small black hole. We're going to look at what will happen if Gardevoir could indeed summon a small black hole. First of all, let's start off with a definition. A black hole, as I've mentioned, is a region of four-dimensional space-time. The reason why I mention four-dimensional space-time and not just space is because of what happens at the singularity. There is the complete gravitational collapse of a system which results in a black hole. The system is, for example, any body that is larger than 3 solar masses, where a solar mass is approximately the mass of our sun. This happens because the quantum pressure of the neutrons actually is less than the gravitational pressure of collapse. And so a black hole forms where there is nothing, that no fundamental force that can overcome that gravitational force. Now, suppose that the mass was less than 3 solar masses, then normally, because we'll come onto solar masses, or we'll come onto black holes that potentially are less than 3 solar masses, but normally, an object that is less than 3 solar masses that is collapsing will actually be overcome, will become stable by the quantum pressure of neutrons. That quantum pressure is essentially the force, the fundamental force of repulsion between neutrons. And so what would happen is that celestial object, which is normally a star, would become a neutron star. So when a star undergoes a catastrophic event, such as a supernova, that's at the end of the life cycle, the excess material is obviously shed, and that's what we see as the supernova, detected by telescopes. But the remnant that is left, becomes a neutron star or a black hole. The interesting thing about black holes is that they are very simple. In fact, they are only characterized by, at most, 3 properties: their mass, angular momentum, and electric charge. And this is called the no-hair theorem. The idea being that hair is very complex. If an if a problem is hairy, it's typically means that it's complex. It's a colloquial way of saying that it's complex. And so no hair theorem suggests that a black hole is not complex. It can be completely defined by just three properties. In other words, whatever goes inside a black hole is reduced to just these three properties. In essence, the matter that enters a black hole is converted. So, an object that has color, for example, will enter the black hole and it will lose that color, and it will only contribute to the mass, the angular momentum, and the electric charge of the black hole. However, not typically the mass, angular momentum, and the electric charge are already defined once the black hole is created. And really, the mass is the only thing that can change from matter entering it naturally. However, this is perhaps not a perfect description of black holes, and maybe black holes are actually more complex than we originally imagined. And that's simply because there's no quantum theory of gravity, essentially, no theory of everything that allows us to understand exactly what black holes are. And so we can't actually grapple with a full description of a black hole. This is simply because our current classical model breaks down at the singularity. And the singularity is essentially the center, the very center of the black hole, where where scientists and people alike have come up with simply contrived ways of describing the singularity, such as having infinite density, time stopping, and so forth. But we're going to come to this more when we talk about singularity in a moment. So, as I said, they form by a supernova. So, when a star dies, it doesn't necessarily have to undergo a supernova. For example, our star most likely will not undergo a supernova. It will probably become a red giant for sure, but then it might become a dwarf in the end, a white dwarf, and then it will essentially fade into nothing. But a star that is much larger than our star, than our sun, can become a red supergiant, and when that finally has come to the end of its life, it can explode dramatically into a black hole or a neutron star, and at the same time, a supernova will result from that dramatic end of his life. So what happens is essentially the elemental composition of the star. For example, it could have a lot of heavy elements because it's a larger star. If that's the case, then it's going to erupt, and that's what causes the universe to have heavy elements. For example, any element that is heavier than iron will typically be formed by a supernova, because it's only from those original stars that such heavy elements could form in the first place. But at any rate, when a star undergoes a supernova, it sheds that material out, and then the gravitational attraction around the remnant is so intense, much more intense than the gravitational attraction to a smaller star. essentially the distortion of space-time, that's going to collapse the gravitational force. The space-time around such a star is so warped that there's actually going to be a gravitational collapse, and it's going to result in a potential singularity. And so black holes simply form from stars. And as a result, maybe you are aware that there are countless trillions, quadrillions of stars in the universe, and of those stars that are of sufficient mass, a black hole could form. And so there are many trillions of black holes in our universe. For example, there are billions of black holes. However, there is one supermassive black hole in the center. We're going to talk about supermassive black holes in a moment, but a supermassive black hole typically is at least 100,000 stellar masses. Okay, let's talk about the features of a black hole. Many of you will know that there is a point at beyond which you can no longer escape the gravitational pull of a black hole. This region is called the event horizon. It's essentially the circumference of the black hole, the limit, although there is no hard limit of a black hole. So if you are just a little bit outside of the event horizon, you will still feel the pull of the black hole. It just means that you might be able to escape if you're light, for example. If you're traveling at light speed, then you could escape beyond the event horizon. But if you were just standing still a few meters away from the event horizon, or even a light year away, perhaps, you would still feel the pull of the black hole. As soon as you cross the event horizon, then there is no going back. There is only one fate for you, and that is towards the center of the black hole. We're going to talk about what happens at the event horizon, and the strange thing about the event horizon is that there is no way to actually see, for an external observer, someone outside the event horizon, there is no way for them to see what happens inside, beyond the event horizon. So essentially inside the black hole. And the reason for this is because, as I said, light can't escape from a black hole. And so necessarily a black hole cannot emit radiation. As long as there is no radiation that can move faster than light, and we haven't discovered any such radiation, so a black hole would be completely invisible. But at the singularity and at the event horizon, time stops. So when an object approaches the event horizon, to an external observer, that person, that object, hopefully it's not a person, but that object, even that radiation, will obviously emit or reflect light to our eyes so that we can see that object. And what happens is that the reflected light becomes more and more redshifted. So it becomes redder and redder. The reason for it becoming redshifted is simply because that space-time is being stretched, and the light is essentially traveling. The wavelength of the light is going to be increased, and it's going to result in redshifting, just in the same way that expanding space causes redshifting. Now, at the same time, time is dilating. Time is dilating for the observer. However, the object, and let's just say it is a person, so that we can give him a sentience, the person will actually be able to look at his or her watch, and time will not be moving any differently to how it was before. But to an external observer, that person will be slowing down. With obviously that is counterintuitive. It would seem like he should be speeding up, but actually he's slowing down closer and closer to the event horizon, exponentially so. And so what happens is that at the very limit of the event horizon, the person stops moving because time essentially freezes. Time becomes so dilated, and the reason for this dilation is essentially because this is the point where light can no longer break free, can no longer travel away from the event horizon. This is, remember, the event horizon is that boundary whereby light can, nothing that travels above or nothing that travels below or at the speed of light can escape from. So at the event horizon, light is essentially going around. What I mean by that is that at the event horizon, light cannot travel out of the black hole, but any light that is in that event horizon is essentially confined, trapped, imprisoned in the event horizon. And so the light will be circling around forever on the perimeter of that event horizon, on the circumference of the black hole. And this is essentially why why depictions of black holes depict light being warped all around the black hole. This is known as gravitational lensing, which will come onto to talk about how black holes are actually detected, although there are several ways of detecting black holes. But let's now talk about the singularity. So after the okay, so yes, the light traveling from the person who is at the edge of the black hole no longer is able to meet up with us. And so what happens is essentially the person's view begins to fade. It's like an after image. The person is no longer there in a sense, because remember, the person's clock hasn't slowed down whatsoever. It's still going tick tock at the same rate as it was before, but now the observer of that person is observing him as time stopping. The way that this paradox is resolved is that the person who is at the black hole, the person who is at the circumference of the black hole, immediately and all in one single moment, sees the entire future of the universe in one go. Because remember, the person who is observing the person at the black hole is obviously going to eventually do something else and maybe have children or go back to Earth or whatever. And everything else is going to happen. New stars are going to form, and new black holes are going to form. The universe is going to continue progressing. Meanwhile, this person, let's say the observer comes back in 10 years, or the observer's grandchildren come back, they're still going to see him at that same place. So for the person who is there, he or she is actually going to be a witness to the complete progression of all states in the universe. Well, will the observer always see the person there? Because after all, where is the light coming from? Since new light that enters the black hole or crosses the event horizon will technically not reflect from it, because as I said, it's like an after image. So there's nothing there. So what actually happens is that the image of the person is actually just going to fade away slowly with time. This is an interesting feature of the event horizon. And so the event horizon is essentially a solution of uh, of the equations. I think of Einstein's field equations that describe a black hole. The other solution is the singularity, and at the singularity, things are perhaps more dramatic, more interesting, because time stops again. So yes, time stops in two different places, which seems unbelievable. How can time stop at the event horizon and then time stop again at the singularity? But remember, that's just for external observers. For the actual person who is traveling into the black hole, time doesn't stop at the event horizon. And even at the singularity, we don't know, of course, what happens. It's possible that time stops even for the person inside the black hole, but it's possible as well that there is a hypothetical white hole on the other side of the black hole. So the idea is that a black hole collects information, assimilates information, gathers matter and radiation, and the white hole rejects, expels information. So it's like there is a gravitational well that is invisible, a gravitational well into the black hole, and then at the singularity, it's asymptotic. So the gravitational potential at the singularity is infinitely deep, according to our current understanding. But then at the other side of that, which perhaps doesn't make any sense, because if something is infinite, then there's no other side. But at any rate, potentially at the other side, hypothetically, there is a white hole where the asymptote is flipped on its head. The gravitational potential is infinitely high, and it's essentially impossible to go inside a white hole, even for light. But anything that is at or below the speed of light will be expelled from the white hole. As I said, that's just hypothetical. At the space time perhaps freezes, perhaps doesn't. And again, the reason why we don't know for sure is because we don't have a quantum theory of gravity. Because with quantum, with quantum, this is obviously a quantum property that would define what happens at the singularity, because the singularity is said to have infinite density and be at a single point. Quantum theories are able to explain things that are not well defined, and in this case, a black hole is not well defined in the sense that we don't know technically what happens at a black hole. Of course, we can calculate it. We're never going to go inside a black hole and then come out and then record what's happened, but rather we can infer and use mathematics and our tools of science to deduce what happens at the black hole. inside a black hole. All we know for sure is that when information enters, and information is matter and radiation, when energy enters, no energy is released. This is not to say that the black hole attracts energy, but rather that space-time is so heavily distorted around the black hole that it's only natural for things to space-time is so heavily distorted around a black hole, and at the pinnacle of that is at the singularity, that because everything, and we're going into space-time now, because everything travels in straight lines through four-dimensional space-time, 3 dimensions of space, 1 dimension of time, everything moves in straight lines through space-time, and so when space-time is warped, everything still moves in straight lines. And so the warped space line becomes essentially a new geometry, and so a new path that seems curved, but actually the object, the information, still travels in straight lines on a straight trajectory, but rather through curved space-time. And so in a black hole, the space-time is so curved that essentially the ability for things to move out of that black hole ceases to be. And so everything can only go in straight lines towards the center. There are no paths outside of the black hole once you're already inside it. The other thing about a black hole is that it can have an accretion disk. And an accretion disk obviously comes from the word accrete, which means to gather. Normally, the way that black holes accrete matter is when they're in a binary system and there's a star in the vicinity, stellar wind from that star will be accreted into the accretion disk of the black hole. And the accretion disk obviously is necessarily outside of the event horizon. And this is where I can just briefly talk about the Schwarzschild metric. The Schwarzschild metric defines the smallest distance from the center to the event horizon. And this is known as the Schwarzschild radius. So the accretion disk will accrete with a distance equal or greater than the Schwarzschild metric. Now remember, if it's equal to, then that's at the event horizon. That matter is actually going to be stuck in time, essentially, to an external observer. So even if you took out all of the matter from outside of a black hole, you would still be unable to remove the accretion disk completely, because at that event horizon there would be matter that cannot escape because it's traveling at the speed of light, or it cannot escape because light traveling from that matter is not even able to escape. So that matter is actually going to be confined to that event horizon for an indefinite period of time, and until the light fades away. Now let's suppose that it's a supermassive black hole. If that's the case, then the matter from the matter that makes up the accretion disk can actually be from the interstellar medium. So it can come from elsewhere. So with that, let's talk about the different types of black holes. And there are about 5 types, I say about because some of them are hypothetical. In fact, most of them, 3 out of 5. The stellar black hole is the most common by far. That is the black hole that is at least 3 solar masses, but can be up to 100 solar masses in size. And this one is made by the same way that any black hole is made, a supernova. Although there are other ways that black holes can be formed, which I will talk about before long. A supermassive black hole is one that is made by a star that is 10 to the power of 5 stellar masses, or 100,000 stellar masses, or beyond, essentially. There is no upper limit to the size of a black hole, but typically we've seen black holes that are at least supermassive black holes that are between 10 to the power of 5, so 100,000, and 10 to the power of 10, or 10 billion stellar masses. Normally, these types of black holes are found at the center of galaxies. And just as an aside, it's very rare for a black hole to form outside of a galaxy. So basically by itself. Because a black hole is a star that has died. So unless a star can form outside of a galaxy, then it's unlikely that a black hole will be found outside of a galaxy. Naively, we can surmise that the supermassive black holes that we find in the universe are the final product of the life cycle of the heaviest stars. However, supermassive black holes have been found in distant galaxies in the universe where the universe was only 1 billion years old. So if you think about how stars form, how possible is it for a star to have grown so quickly in just 1 billion years? Well, actually less than that, because there was a large period where stars couldn't form, and then form a supermassive black hole, having had to have undergone a supernova. And notice also the supermassive black hole that was discovered, that was detected, was of the order of 10 billion stellar masses. So there are a couple of propositions, there are a couple of proposals to explain how black holes form that are supermassive. First is that early proto-galaxies, so galaxies that were about forming stars, accidentally, obviously galaxies don't have free will, but essentially before they had the chance of producing stars, they instead collapsed and formed supermassive black holes. So instead of a star collapsing, and obviously a galaxy doesn't die as in the same way that a star dies. So an early proto-galaxies could have collapsed into supermassive black holes. The other explanation as to why supermassive black holes form today is that they result from the collision of black holes. So, for example, if two black holes collide, the masses are just going to add together. So that is going to obviously be a black hole that is the sum of the masses of those two. And we've been able to detect black holes because of we've been able to detect the presence of gravitational waves due to the collision of black holes. But nevertheless, even though a supermassive black hole is obviously way larger than a stellar black hole, and would have a larger force field radius as a result. There are smaller tidal forces than a stellar black hole. What that means is that if you were inside the black hole, let's say you were inside a stellar black hole, what you would find is that the gravitational force, the gravitational pull on your head is much lower than the gravitational pull at your feet. Let's say your feet were closer to the singularity. And so you will be stretched significantly. This is known as spaghettification. And you would be ripped apart. But in a supermassive black hole, this phenomenon is less dramatic. So there is, I mean, spaghettification is still going to happen surely, but it's not as great a difference. The gravitational pull on your head will not be as different to the gravitational pull on your feet as if you were in a stellar black hole. And this was counterintuitive to me, but essentially it's because of the equations. When you write down the equations, the size of the tidal forces is proportional to the size of the black hole raised to the power of -2. So now we get to our hypothetical black holes. First is the intermediate size black hole, the intermediate mass black hole, and those kinds of black holes are potentially able to exist, just that we haven't discovered them yet. Just like tachyons, which hypothetically travel faster than light, exist, but or might exist, but we haven't discovered them. They may be expected to form at the center of dense stellar clusters by the merging of different black holes. Although why we haven't discovered them is anybody's guess, but assumedly they're harder to detect. Perhaps because the gravitational lensing effect is too similar to if it was just a star obfuscating another star, for example, coming like a binary star system. That's intermediate mass black holes, and as I said, they could exist, but we haven't discovered them yet. What is more far-fetched is the primordial black holes. In a way, it's more far-fetched, but also perhaps more people believe that there exist primordial black holes. So primordial black holes, just like the primordial soup, which is the beginning of life on Earth, the primordial black hole is like the beginning. So primordial just means like first, beginning, at the start, at the beginning. And in the beginning, obviously there was the Big Bang, and the and because of random fluctuations in the quantum foam, if you will, or more precisely, just the fact that the universe was so intense, the universe was so violent in those times, that black holes just popped into existence. Very small black holes on the order of a few stellar masses or even less, most likely less. And even though they would have evaporated because of Hawking radiation, Hawking radiation being just the release of elementary particles, obviously that was Stephen Hawking that introduced this, and they would eventually fade away completely. But the idea is that today we can detect the primordial black holes because of the Hawking radiation. So we could detect those elementary particles, those photons, electrons, quarks, even gluons. Although how we would detect it is a completely different story. And hence why they're still hypothetical. But essentially, those black holes would be evaporated by now. They would be essentially evaporating today. And it means that we would just be able to sufficiently detect the elementary particles that have been released. And while there would be no more elementary particles coming from the deep recesses of the universe, the early formation from the primordial nature of the universe, we would be able to detect obviously the aftermath. So those particles will still be on their way to us, and so we might be able to detect them. The final hypothetical, and this is truly hypothetical now, is micro black holes. Micro black holes are like black holes that are truly on the order of something you can hold in your hand. Like, imagine you are a scientist and you could just make a black hole. You could make a black hole that could fit in your hand. And this is what we're going to talk about with Gardevoir. But essentially, imagine that. Imagine how unstable such a black hole would be. They would quickly evaporate. Moreover, when a micro black hole finally fades into nothing, it doesn't just go like that with a poof. It bursts with a sudden burst of particles, and the micro black hole indeed explodes, just in the same way that a star explodes when it forms a black hole. But obviously, in this case, no star is going to form a micro black hole. Remember, a natural means of producing a black hole using stars is only feasible, is only viable if that star is at least 3 solar masses. So about 3 times the size of our sun. So we won't expect our sun to become a black hole. So Gardevoir can make black holes. It says in the Sapphire and Alpha Sapphire Pokédex entry that Gardevoir has the psychokinetic power to distort the dimensions and create a small black hole. This Pokemon will try to protect its trainer even at the risk of its own life. There are some other very interesting Pokédex entries as well. Like, it can't feel the pull of gravity. It supports itself with psychic power, and it has the power to predict the future. But let's consider that fact that it can create a small black hole. Definitely, it is possible that there are other dimensions where black holes there are other dimensions that can help to better describe the nature of black holes, or in which black holes fully exist. But for our current view of four-dimensional space-time, black holes are sufficiently in existence. They that is to say that Gardevoir could potentially form black holes using different dimensions, using strange dimensions, but it's not necessary to create a black hole. What is definitely necessary is to expend the energy to form matter. And this is known as the energy mass equivalence. And most people will know this as E equals mc squared. Of course, this is Einstein's famous equations, which is not to be confused with the field equations that I made reference to earlier. But if a black hole is about the size of a human being, and Gardevoir is about the size of a woman, um, and so Gardevoir was if Gardevoir made a black hole using its own matter, its own body mass, then it makes sense since it does say that it will protect its trainer even at the risk of its own life. So perhaps it will die surely if it uses its own body mass, but it's all in the name of protecting its trainer. So perhaps it's not something that it will really think twice about. But let's say it does that, the force field radius is going to be on the order of 10 to the power of minus 25 meters, which is 10, which is 0.24 zeros and then 1. That is much smaller than the nucleus of an atom. So that such a black hole, nobody is going to see it, first of all. Well, nobody will see a black hole, but nobody will see the effect of the black hole because it's so small. And the second of all, it's just going to instantly disappear because of Hawking radiation. There won't even really be much of an explosion because there are very few things that are smaller than the nucleus of an atom. So it's just going to be like a few subatomic particles that is released, and it's not really going to do any harm because the energy of those particles is going to be equal to the energy of the black hole. However, if, let's say, Gardevoir is able to pull the mass of the sun, then the Schwarzschild radius is then going to be about 3 kilometers or 2 miles. And if Gardevoir is able to do that, then the whole world is going to be destroyed. First, anybody who is within that radius is obviously going to be completely destroyed by spaghettification because they'll be in the radius of 3 kilometers or 2 miles. But then, as matter continues to fall into the black hole is going to continue to increase in size. And eventually, it's going to consume the entire Earth. And then probably once it's done that, it will consume maybe the other planets as well. Probably the moon and then the other planets. Or alternatively, it will just take the place of the Earth and then the moon will be orbiting this black hole and nothing else will happen. Let's say Gardevoir can indeed distort the dimension such that once it produces the black hole, it can just conceal it within a dimension that is higher than the 4 dimensions that we're used to, and it won't cause anybody any harm except for that one moment. But even in that one moment, as long as they are in a 3 kilometer or 2 mile radius, they're going to be destroyed. So ideally, Gardevoir will produce a black hole that has just a radius of 1 meter, let's say. If Gardevoir aims to do that, then it can do that with a mass that is about 100 times the size of the Earth. So 100 Earths. And if it did that, then it would produce a black hole with a force-field radius of 1 meter. And in that case, it could indeed just push the black hole using its psychokinetic powers to the offender, who is assumedly trying to maybe kill its trainer or something. And yeah, it will definitely rip off his arm or whoever's arm, or maybe it's a different Pokemon, then it can destroy its legs or arms or whatever. And obviously, if Gardevoir pushed it right through the offender, then that's going to just completely destroy the person or the Pokemon. That Pokemon or person is going to die because the heart is going to obviously be consumed within the black hole. And let's say Gardevoir wants to produce a black hole that is 10 meters across, so a force field radius of 10 meters. This is going to equate to 1,000 Earths, so it just scales linearly. And this is also about the size of Jupiter, the mass of Jupiter, rather. Remember, there's not going to be a difference necessarily between this black hole, this micro black hole, which could be 10 meters, 1 meter, anything you like, really, and normal black holes, stellar black holes that are formed by natural means. Because remember, there are only 3 things that define a black hole. Only 3 things that we're aware of, at least. The mass, the angular momentum, and the electrical charge. Now, for all intents and purposes, it's easy just to think about the mass and the angular momentum and the electric charge being 0. This is known as a force-filled black hole. But there are obviously other kinds of black holes, other solutions, where the solutions of Einstein's field equations were the event horizon and the singularity. For a black hole that has angular momentum or electric charge, those solutions will look different. And so we haven't discussed those. Those are going to be outside of the scope of this episode. But Gardevoir could make any kind of black hole. So it could be with electric charge, it could be with angular momentum. Definitely, I'm sure with its psychokinetic powers, it could just make that black hole start spinning and give it angular momentum. But yeah, again, I'm just focusing on the relatively easy, straightforward black hole that just is defined by mass. Now, if Gardevoir could indeed manipulate space-time, manipulate dimensions using psychokinesis, which just means moving using psychic powers, kinesis is moving, then what does that mean for people who are in the vicinity of Gardevoir? It could lead to protection or it could lead to destruction. Suppose that Gardevoir produced or manifested a dimension that caused space-time to break down. Then that is obviously destruction. But suppose that Gardevoir could actually localize that and produce a dimension around the offender, and then at the same time be able to close that dimension as well, or be able to unmanifest it. Then indeed it could be used as protection. That whatever offender will now be trapped in that dimension and will not be able to encounter the natural world anymore. Perhaps it will still be living, just in a different dimension. And it could be a different parallel dimension to ours or to the Pokemon world. Or it could actually just be a dimension where nothing is taking place, nothing is happening. Kind of like, imagine you were locked in the length dimension. just one dimension of space, and you couldn't move side to side, you couldn't jump up and down, you were just a one-dimensional creature, then in that same way, you could still encounter the world. It would just be a completely different experience, and nobody would be able to detect your existence really. Just like we aren't able to detect something that is truly one-dimensional in nature. As we've already said, the effects of black holes is time dilation and gravitational lensing. So Gardevoir, when it produces black holes, suppose that the offender now is trapped inside the black hole. Well, at the event horizon of the black hole, which is just whatever Schwarzschild radius of the black hole is, that circumference, the time is going to stop for the external observer. So for the person, the trainer that Gardevoir is protecting, the offender is still there, actually not having yet been consumed by the black hole. But nevertheless, it is being consumed by the black hole. At the same time, that offender is seeing exactly everything that will happen, but all in one single moment. Because in the very next moment, which is actually at the same time, basically, or as quickly as Gardevoir is able to push the black hole into the observer, but recall that the observer, the offender rather, but recall that the offender or any matter that isn't traveling at the speed of light or that is traveling at the speed of light or below is going to enter the black hole. And so the inside the black hole, the offender is accelerating towards the black hole, towards the singularity, towards the center, and at the center again, time stops according to our calculations. But for Gardevoir, if it's produced using perhaps more exotic laws of physics, a different dimension, then it could actually be different. And indeed, maybe there is a white hole. So it could be that Gardevoir is actually performing a kind of teleportation where the offender goes into the black hole but is ejected in a white hole somewhere else. Kind of like how Hooper has its rings, and its rings can be a portal between different places, a wormhole, if you will. However, that's tangential to the discussion for today. And just with gravitational lensing, the idea is that, as I said, the idea is that at that close to the black hole, close to the event horizon, but obviously not inside the black hole because no light can escape, no information. At and close to the black hole, there's going to be heavy warpings of space-time. So to the trainer, he or she is going to see the offender being stretched and warped in different strange ways, and probably an accretion disk is going to form made of, let's say the black hole is going straight for the heart, maybe the legs will become part of the accretion disk. But certainly it will be like where before the offender, let's say it was a person as well, the person was standing upright. Now it will seem like the head is somehow curved round and the legs are curved the other way. And so it's kind of like curved around the black hole. And it's actually through gravitational lensing that we were able to discover, and obviously we is the scientists who discovered them, the astronomers, they were able to discover detect rather, the largest black hole, the largest black holes, using the fact that light is seemingly travels in curved lines through space time. Remember, they travel in straight lines, but because space time is curved around the black holes, that they seem to take curved paths towards us. So stars that are that should be that stars whose light should be traveling to point A are instead traveling to point B because of the curved seeming nature of the curved trajectory due to gravitational lensing. Okay, we've come to the end of today's episode, so let me finish with some myths and then the outro. And so, myth one is that black holes have infinite density at the singularity. The reason why I say this is a myth, although it's not proven, it's not certain that black holes, what happens actually at the singularity, but it breaks down. It means that it means we're conceding that the laws of physics break down at the singularity, which doesn't make sense. The laws of physics should hold everywhere. Why should the laws of physics break down? Even at the start of the universe, the laws of physics didn't break down, just that there were more exotic properties that manifested and gave rise to the phenomena of the early primordial universe. But today, we have our relatively stable laws of physics, our relatively stable phenomena that we encounter. But at the point of the singularity of a black hole, there should also be something happening. It should also be defined. So if the black hole has infinite density at that point, it means that infinity should be well defined. And by definition, infinity is not well defined, it's an idea. So black holes, as long as they are well defined, and they definitely are, we even have a picture of an actual black hole, and then there can be no discontinuity, like there can be a mathematical discontinuity in a black hole. Black holes are like the vacuum cleaners of the universe. This is not true simply because black holes are just entities that have space-time warped around it, and everything travels in straight lines through space-time. So if something is traveling through a straight line and the straight line is going towards the black hole, then whereas outside of the black hole, that object could turn round. And when it turns round, it's only because there's a force applied to it. So essentially, due to Newton's first law, unless there's a force applied to it, that object is going to continue in that same trajectory. Or obviously, if it's not moving at all, then it's not going to move. It's not going to just spontaneously start moving. However, we can still detect apparent movement because of expanding space, but that's outside of the scope of this episode, and we're almost at the end here. So thank you for your patience and for staying with me on this journey. Everything is destroyed at the singularity. This probably is not the case. Theoretically, the spaghettification would destroy any matter before it reaches the center of the black hole. But at the center, at the singularity, it's possible that either time stops, so nothing is destroyed because time no longer runs, Or there is the white hole, and at the white hole, time is essentially reversed, and so matter is ejected. Now, nothing is destroyed in the universe in the sense that a particle does not disappear from the universe. So nothing is destroyed in that sense. Everything will just be reorganized. All particles will be reorganized into different objects. So a human made of so many particles would still just become a soup of that same number of particles, such that if it were released outside of a white hole, then it would still the number of particles would be the same, at least in theory. And the final one is black holes are black. This is easy. Black holes are not black in the same way that my microphone is black. Black holes are invisible. The difference is that black objects absorb light, but invisible objects do not absorb light. Rather, light passes through them. So you don't see anything. Like, I can see my microphone, but you couldn't see a black hole. The reason it looks black is because the rest of space is black, but the region of a black hole is such that, well, in this case, obviously, light doesn't pass through it. Rather, light from all directions goes in and doesn't come out. So we don't see any reflection of light. We don't see the light coming back into our eyes. Rather, we have to detect it using other ways, such as I mentioned, gravitational lensing, and perhaps even gravitational waves, such as when two black holes collide. If you've come this far into this episode, please consider liking it on Spotify, Apple Podcasts, or wherever you listen to podcasts. This will help me tremendously and cost nothing but a few moments of your time. Today we discussed black holes. We talked about how black holes form, how they're characterized, the key features of a black hole, event horizon, singularity, space-time, the accretion disk, different types of black holes, and the hypothetical types of black holes, and how Gardevoir could manipulate space-time dimensions to make black holes for itself. You can find the resources I consulted while researching for this episode in the show notes. Isn't the power of science simply amazing?